Welcome to Cobem 2021-0475 paper, Automated Machine Learning Approach Applied to Nuclear Energy Generation Short-Term Forecasting, by Jorge Gustavo Sandoval Simão, Viviana Coco Mariani, Leandro dos Santos Coelho, from Pontifical Catholic University of Paraná, in Brazil. As an introduction, we say that in this study, it's about US nuclear power plants energy generation short-term forecasting. These nuclear power plants maintain a consistent share of about 20% of the total annual United States electricity generation from 1990 through 2019. They are 96 power plants divided in two clusters, C0 and C1. Its energy generation were divided in two clusters because some of these power plants were consistent and another were erratic in the energy generation. So to have better machine learning readings and pattern recognition, we divide it in this C0 and C1 clusters. RreliefF was used for feature selection in both clusters. And for the forecasting model, we use AutoML with coefficient of determination. In this figure, you can see the analysis of the data set divided in 12 months, the period, and the energy generation pattern for the whole 96 power plants. The raw data set used for this research was obtained from the US Energy Information Administration page, and the version used in this study is available on Kaggle for future research. The whole data set contains the power generation from nuclear power plants in the United States of America, separated by federation between January 2013 and November 2020. Its robust data comprises 9 files containing monthly energy generation, separated by nuclear power plants in each of the US states. In this figure, it's possible to observe that except for month 12, December, in this case represented by the number 11, the rest of the distribution tends to a right tail and is not a Gaussian in this X structure. That's why we use the power transformation function after the cluster dataset, which was helpful in stabilize variance and make the data more normal distribution-like, and improve the validity of measures of association such as Pearson correlation between variables, and for other data stabilization procedures. Here is the forecasting model that we used in this work. Here we have an application of AutoML to short-term electric load forecasting tasks. From a data science perspective, the biggest challenge is to develop advanced pipelines of algorithms covering numerical dynamic data application. And this AutoML uses Bayesian optimization on top of scikit-learn for generating machine learning pipelines. It uses SMAC, sequential model-based algorithm configuration, as the underlying Bayesian optimization method to optimize the machine learning pipeline pre-processing automatically and post-processing method selection, model selection, and hyperparameter optimization. So this automated machine learning used with our data set found the best results represented by our performance criteria. We used this automated machine learning method in 2 clusters, as said before. And here we have the results of the 2 functions applied to the dataset. Both functions have an ideal number of clusters out of 5. We have an album function and a CUH function. This number was tested, these 5 clusters, but was found that the AutoML model maintains accuracy even with the division into 2 clusters, which shows that the sudden drop in inertia in the factor that really influences the accuracy of the model. So we kept it in 2 clusters because it was easy to determine the constancy of the energy generation. 5 clusters was the ideal following the elbow and the CUH function. However, they were very near to the 2 clusters result efficiency and resulted in models with a very, very high precision rate. Feature selection tests were performed after normalization, and the objective was to find, for each of the clusters, the number of features needed to generate the model as accurately as possible. To achieve this goal, the AutoML was wrapped in the RreliefF technique to find out which was the most suitable combination for each cluster. And this table presents these results: the coefficient of determination for each feature in each cluster to a maximum of 11. Once the best number of features for each of the clusters was found, the model with the best results for each of them was run, and its metrics were analyzed, as shown in this table. For cluster C0, 11 features were used, while 9 were used for cluster C1. As shown here, the division of energy generation patterns into clusters allowed a closer fit of the model, allowing for greater precision. So we have very, very near results because we separate it into these clusters. When they were not separated on the first tries of this research, we had a very, compared to this result, a very low precision. So when we combined it with similar patterns, the automated machine learning reached coefficients of 99 in train test and valid and 0.005 in train and 0.002 in test and valid in some features, of course, to the median absolute error and for the root median squared log error, showing that even the erratic power points, they follow a pattern. So, as a conclusion, the generation of nuclear energy follow patterns that vary from one point to another, depending on its activity. Some generation patterns are more constant, others more erratic. With clustering methods, it's possible to define these patterns. With techniques such as feature selection and AutoML, the power generation pattern can be identified and predicted. The AutoML proved to be able to predict trends in the 2 clusters used in this study, as well as feature selection methods were able to successfully identify the most important variables to be used. These techniques together can efficiently predict the energy generation of nuclear power plants, and that cluster increases the percentage of the correctness of the models by efficiently separating the generation patterns. And here ends this paper presentation, and thank you for watching.